nearly there. Just one more connection to the primary booster circuit. Oh, that's done it. No light, I can't see a thing. Oh, some light, I can see again. What's your problem out there?
Hi, Stella. We've got another question for you. Why can you see a cat's eyes in the dark?
They glow, don't they?
Yeah, they're really bright. I think it's something to do with them being able to see in the dark. Well, cats can see in the dark, can't they? It's because their eyes shine.
I don't know. We need science in action to investigate.
I'm onto it. My dark lab seems the perfect place to start. Maybe Boffin here can help. So why can I see her eyes in the dark? What else can I see in the dark? Shiny things? White things? But it's not really dark though, is it? My torch is on. Interesting. In the dark, I can't see anything at all. We need a source of light. Boffin's eyes only appear to glow. They're actually just reflecting the light from my torch. The light from the torch reflects off Boffin's eyes and enters mine, so I can see them. Without a light source, I can't see anything at all. Trish takes over this dark investigation.
Tonight's investigation starts here at the Transport Research Laboratory. And believe it or not, this is the laboratory. Anyway, I'm here to find out how to be seen at night.
These might look like ordinary roads, but this is actually a private road network reserved for trials and experiments.
Oh no! Great start. Oh, I have to leave this here, I'm afraid.
I've arranged to meet some experts on the dark, but I've got to find them first. They aren't far away, but will they see me?
Oh, brilliant. It's a road sign. Oh, great, a car. These car headlights should reflect off the sign so I can see where I'm going.
Too busy peering at the road sign to realise I've found my experts. Well, they've found me.
Hello.
Hi, Trish.
Hi.
I'm Roz, and this is John from 3M Company.
Aha, my experts on being seen in the dark.
And it looks as if you could do with some help in that department.
Yeah, my bicycle light packed up.
And that's not the only problem. The clothes you're wearing, they don't help you to be seen either.
Yeah?
Let me show you.
Roz's jacket certainly looks brighter than mine. That's because different materials reflect light in different ways. Roz's yellow jacket reflects more light than my dark red one, so you can see it more clearly. But that's not quite the end of the story. John's grey jacket looks rather dull, doesn't it? Even with the headlamp shining on it, it's not that bright looking at it from this angle. But look at it from my point of view, from inside the car. The bands on John's jacket are made out of a special material which reflects light in a particular way. Instead of being scattered in all directions, when the light from the headlamps reflects off the banding, it all reflects back down the same path, straight to the driver's eyes. More reflected light reaches my eyes from John's jacket than Roz's, so it looks much brighter. The material is called retroreflective. This retroreflective banding is ideal for pedestrians at night. Because all the light from the car's headlamps reflects directly back into the driver's eyes, it makes it look a lot brighter than ordinary material. The light from the car headlamps falls on a road sign, but from the roadside the effect isn't that impressive. But look at the view from inside the car. The signs look really bright. Nearly all the light from the car headlamps is reflected back off the signs to my eyes. That's because the signs are made from retroreflective material too. But even the best reflective gear doesn't work if there's no light source at all. But this garment can be seen, the Illumivest, invented by Jeff Pinkney. Jeff, hi. Listen, this Illumivest is brilliant. It is great.
Do you like it?
Yeah, it's well wicked. Yeah. Well, listen, who's going to be wearing it?
Well, anybody can be wearing it during the hours of darkness. Cyclists, motorcyclists, tunnel workers.
So it's its own internal light source. It can be seen in the dark. It doesn't need an external light source.
Yes, it works with fibre optic cables, which are woven into the material. They transfer the light from the light source through the material.
Well, listen, I don't know about motorcyclists, but I think we look pretty groovy together. Here's me in my retro-reflective jacket, and you with your Illumivest. I think we should hit the disco, don't you think?
Well, why not? Yeah.
Yeah, I think this is going to be the in thing. Yeah, definitely. I reckon Stella might find a use for that retro-reflective banding.
Looking good. It's important I'm seen up in space, and this retro-reflective banding should do the job perfectly. So long as whoever's out there has a light source to shine at me, I'll be seen. But maybe my own light source is a better idea. Then I can see anyone else out there. I'll be able to see anything it reflects off. And they'll be able to see me. The only things you can see are either a light source or an object which reflects light.
What about a light beam? You can see that.
Yeah. Look at those searchlights. They're massive light beams.
And torch beams.
You can see those, but what are they?
They're just light, aren't they?
Yeah. But what are you seeing when you see a beam of light?
You can see the beam of light by adding smoke. What you're actually seeing is the light reflecting off the smoke particles. Whenever you think you're seeing a light beam, the same thing is happening. You're seeing the light reflecting off droplets of water, dust, or particles of smoke. Using smoke like this helps you to see that light always travels in straight lines from the light source. But something's worrying me. Light travels in straight lines, but if light travels, it must take time to get to its destination. So how come our reflections aren't late? After all, the light has to travel from me to the mirror and back again to my eye. Why isn't there a delay between my actions and what I see? We don't expect our reflections to be as late as this, but actually there is a delay. But because light travels so fast, it's too tiny to notice. So just how fast does light travel? Another investigation for Trish, I think.
To find out just how fast light does travel, I'm going to send light on a very long journey. Longer than this, longer than this, longer than this. I'm going to send a beam of light into space. This is no ordinary beam of light. This is a laser gun. It will fire a very intense beam of light, laser light, up into the air. The light is so intense that once fired, it can travel thousands of kilometers into space. the light will travel to a satellite thousands of kilometres away.
How will we know when it's got there?
Believe it or not, this is a clue.
A disco mirror ball? What's that got to do with it?
Roger Wood, a scientist at the Hertzsprung Satellite Laser Ranging Base, revealed the connection.
This is actually remarkably like a real satellite.
Yes, satellites can be as small as that.
Well, some are even smaller, but this is a typical sort of size. And in real satellites, the flat mirrors that you see here are replaced by retroreflectors.
Ah, retroreflectors. So that means the beam of light that actually arrives at the satellite will reflect directly back down the same path.
That's it.
At least I've learned something. The laser light bounces off the satellite and reflects back down to Earth. Not just anywhere, it's going to come back right here. This is a receiver which signals when the light returns.
The precise position of all satellites is calculated by a computer. This computer graphic shows their orbit, so we know exactly when they're passing overhead. At 9:30 tonight, a satellite called Epsilon is going to pass over us, and our laser beam's going to get it.
The light is going to have quite a journey. To Epsilon and back is 40,000 kilometres. Nearly 9:30. Here it comes, and it's off.
Woo! There it goes on its 40,000 kilometre journey. Right, Rog, how long do we have to wait for it to come back?
I've got news for you. Come and have a look downstairs.
Of course, when you see a laser beam, you're not seeing the laser itself. What you're seeing is the laser light reflecting off dust and water droplets in the air.
So we've got equipment here that can measure precisely how long it takes for a burst of laser light to get from here to the satellite and back again.
But the big question is, how long does it take?
Well, it's about 1/7 of a second.
Wow, 1/7 of a second to travel 40,000 kilometres.
That's right. And you can get a very vivid idea of how long 1/7 of a second is by listening.
These clicks are 1/7 of a second apart, and in that time, light can travel the same distance as once around the world. That's fast. In fact, the speed of light is an amazing 300,000 kilometres per second.
But you know, it's not just laser light that travels this fast. All light travels at this incredible speed, even the light from my humble torch.
Wow, that's really fast. So what about light that's travelled even further? Light from the moon. The moon is 400,000 kilometres from Earth. The speed of light is 300,000 kilometres per second, so I can calculate it takes 1.3 seconds for moonlight to get to us. That means what I see on the moon now happened 1.3 seconds ago. But of course the moon isn't a light source. What we're seeing is light which has travelled from the sun, reflects off the moon and enters our eyes.
On Earth, we see things because light reflects off them and enters our eyes. In space, the same is true. But in space, the distances are much bigger. I'm off on a journey to show you exactly what I mean.
Follow out.
The moon and planets in our solar system only appear to shine because they're reflecting sunlight back at us, but they have no actual light of their own. What we see from Earth when we look at the planets in our solar system is light which has travelled from the sun to the planets and back to us on Earth. But it's another story outside our solar system.
Travelling beyond the frontier of our solar system, there are 100 billion stars in our galaxy, of which our sun is just one.
Stars are huge globes of burning gas, just like balls of fire. Stars are light sources, just like our own sun. The light from stars takes time to travel through space to reach us on Earth. Sirius is a fairly close neighbour and one of the brightest stars, but it still takes light nearly 9 years to travel from Sirius to Earth. So travelling to Earth from Sirius at the same speed as light, it's taken virtually 9 years to get to Earth. Good job I packed my sandwiches. My next starting point is the star Capella in the constellation of Auriga the Charioteer. Capella is the 6th brightest star in the heavens, but it's even further from Earth. If I'm travelling from Capella at the same speed as light, it's going to take 46 years to get to Earth. Oh, I'm definitely feeling a bit jaded. I look just like my nan. If you think the stars in our galaxy are a long way off, the Hubble Space Telescope is able to view galaxies even further away. These pictures show the Eagle Nebula, but it took the light 7,000 years to travel to the telescope from the stars. Just imagine how far away they are, or were. It's a bit like looking back in time. What we're seeing now is not what's there today. Because of the time light takes to travel to Earth, what we're looking at is galaxies as they were over 7,000 years ago. So when the Eagle Nebula looked like this, Stone Age man was living on Earth. I wonder what it looks like now. See you in 7,000 years.
That's what she thinks. Meanwhile, I must get back to repairing those circuits. But here's something else for you to investigate. What's going on here? The words read carbon dioxide, but through the stem of the glass.
It's upside down.
No, carbon's upside down, but dioxide's the right way up.
Oh, yes. It's when light passes through a glass, the glass turns it upside down, like a lens. But why does dioxide stay the same?
Was it because it's green?